All right, welcome back to round 2. How are you guys doing? Oh, I probably didn't allow you to answer because everyone's muted. So I guess that was just a rhetorical question. Yes, the password is easy to remember for me too, because otherwise I would be lost. Okay, so now we have it's teaching week 1. The recording is going. It's good. And I have about 20 faces in front of me, a list of participants. Let me try. It would be great if you could unmute yourself.
Hello.
Oh, you can unmute yourself. That's great.
Yes.
Okay, so I found that there's a check mark. That's very convenient. So I can allow you all to unmute yourselves. And I think that's a good idea unless it gets out of control. Oh, but I'm the co-host and the host. Okay, I guess that's fine. Any questions before we start? We still have 2.5 minutes. Anything from yesterday that we covered?
Someone's asking if there's going to be a pre-tutorial assignment.
Pre-tutorial. I haven't heard of it. I don't think so.
All
right. Just to remind you, I fixed this issue here. Well, actually, this is now the old. This is the old version, but the new version. Let's see if I can actually. So if you go to modules now and to our section, which is 0501 and 9501, you can see that there is the week 1 version, and this one is updated. This is just the slides, so the notes. I fixed the problem here, and you can also find the annotated version. So that's with everything that I scribbled in there. I deleted some things because they were just too messy, but most of the things I wrote I actually kept in there, so that if you want to look up something that I said in the lecture, then that is available here. And as I said before, the YouTube link there is also available for 1 week. That's class policy to have you only the YouTube link available for 1 week. No, I don't think there's a grade for tutorials. I mean, that should be in the syllabus. So in the syllabus, there should be, if you go down to the grading percentages, yeah, here you can see that. I mean, 35, 25, and 40, that adds up to 100. So this means there's no space available for any percentages for tutorial marks. So by exclusion, no. Okay, it's 10 past. So let's start with lecture number 2. Today I'm going to be talking for 2 hours. So in the first hour, I hope that we will be able to go through vector spaces. And then in the second hour, we will talk about subspaces, and we will have a short break of 5 or 10 minutes in between. Vector spaces built the foundation for linear algebra, so they're the bread and butter. And you can think of them really just as glorified sets, and we talked about sets yesterday. So think about a vector space as a set. I mean, it is a set, as I wrote here, with operations. So they are additional things that you have with a vector space. It's like having additional structure or like additional decorations on a Christmas tree or whatever. So these structures are called addition and multiplication. And this notation just means, as before, that you have input data and output data. So here, when we say V cross V, this just means that if we have two elements, say V and U and V, then this just suggests that the plus operation needs two inputs. I mean, that's very familiar. I mean, we've added numbers. We know to add numbers. And now I'm saying that there is operation for vectors in a vector space, but I'm not saying exactly what it is. So this is the first kind of situation where abstraction comes in, because without saying what this exactly is, we just say there is such a thing, and we have actually a list of 10 rules that we have to follow. So just this notation means two things for an input, and they're both the same kind that we put in, and then this, of course, is the real numbers. So when we use the multiplication, we use a number, a scalar, and then a vector. And what this really is, well, we know that it is in the vector space both times. But in this definition, we don't really say what it is, because that will be an actual example of a vector space. So now that I said, well, I have a set with additional data, and this data is just the operations, we come to the axioms, and this might seem overwhelming because there are 10 rules that you think you might have to study or learn by heart, but really think of them as guarantees. It just really means that whenever you work with a vector space, this is an insurance for you that whenever you do a calculation, it will actually behave a certain way. So it can't go wild, it can't get out of control. This is kind of for your own benefit and not supposed to work against you. So let's go through a few of these. Well, first of all, the first two are very natural to assume, and they're already implicitly assumed in the notation here. It says that if we add two vectors, then we want to get another vector. So it means that it doesn't go out of the set. Remember last lecture, we had the problem that if we apply a function to an integer, it might not be an integer anymore. That way a problem, because we want everything that we do, the operations here should be working on the vector space. The third property is just saying that you can switch the order in which you sum two vectors. Also very natural. This is nothing new for numbers. But we will eventually in this course, in a few weeks, maybe 3 or 4 weeks, encounter operations which do not commute. So they would not have this property of commutativity. So this is nothing that you can take for granted for any operation, but for vectors it is given. Same thing here, additive associativity means that if you have 3 elements and you add them together, then it doesn't matter if you add the first two or those the leftmost two or the rightmost two together. In the end, it's the same. And for this, maybe it makes sense to draw. If you have x plus y plus z, then we first combine these two. This is going to be x plus y. And then we combine these two. Likewise, we could also do this, and then we combine these. And the point is, it doesn't matter which one we do first. The same for the rest of the axioms. They always say that for what kind of input. I use Greek letters here for scalars, and Roman letters with an arrow on top for vectors. They behave a certain way. Any questions about this definition? Anything that's unclear? Okay, so a few remarks. I think the first one I already said. These 10 rules is just something that every vector in this vector space will obey to. So it's for your own benefit that you know you have control over the vectors. The book uses bold symbols for vectors. I don't really like that. It's hard to type in LaTeX, and also you can't draw by hand bold symbols, so it's really just inconvenient. Yuan, you have a question?
Yeah, so what does the X mean in VXV? Because some people are saying it involves V and V, and some people are like, it's a Cartesian product.
V cross V. For now, all you need to know for now is that it means two inputs. So, I mean, you can, I don't know if you ever did some computer programming, you could also have this as an infix operator, where you have plus applied to V and W, and then this would be equal to V plus W. But it just says you can't add one vector to what? That's the problem. So you need two of those. All right. Sometimes I will abbreviate the scalar multiplication, the dot, just a space between no space between them, because that's also done for normal multiplication of numbers. As I said already, I used the word vectors or elements in a vector space. For sets, we just call them elements. And then be aware that vectors, I mean, I suppose that in high school or somewhere in a previous course in area, yeah, is this 2 so you all took 2 to 3, I guess. If this is R2, then we draw them as arrows. So these might be vectors, V and W, and then we can add them together. So this suggests strongly that vectors are something like arrows. And that's fine. That's usually very helpful to a certain extent. But be aware that in this course, we're going to be talking about vector spaces which go beyond this. So we might not be able to always draw them as arrows. This is somewhat limited. And the last point, so for example, functions, we'll see in a second that functions actually define a vector space. And the last point is that for now, notice that scalar multiplication here is always real. So we always multiply a vector with a real number. And this is why we call it real vector space. For now, this is all we need. Maybe later in a few weeks, we'll actually be talking about different numbers. And then this might be a complex number or whatnot. Andrew, you have a question?
Oh yeah, it's still the VXV thing. Is it okay that we interpret it as a Cartesian product? Because someone in the chat said it's not, but I still think it could be, because.
No, that's fine. Yeah.
So is it right to interpret it as a Cartesian product, or is it wrong?
No, that is fine.
So so we can say it is a Cartesian product, right? We can
say
the function is can be listed as like order pairs.
What function?
Like the multiplication and addition. Like we can say it like we can have a set of all its input as and outputs as an order pair, right?
I mean, you will have a pair.
Oh, I mean both of the inputs. Sorry, I mean like both of the inputs, like 1 plus 2, and then we can have an order pair like in the domain 1, 2, like as a Cartesian product of V and V.
Yeah, that's fine.
Okay, thank you.
Okay, any other questions? Then let's get to some examples so that you get a feel for what kind of vector spaces we will be talking about. So of course, the easiest one is the real numbers itself. The real numbers are scalars in this case and the vectors, and they obey all the rules. Oh, this is not good. They satisfy. And this is, I mean, in this case, it's easy to verify because, for example, if you add 1 plus 2, is equal to 3, and 2 plus 1 is as well. But it might get harder in the future to verify those axioms. Okay, the next example is an n-tuple of real numbers. This is usually denoted by Rn, but it's nothing else than just a collection of real numbers, where the number of these numbers is fixed, the amount of numbers. So we always have n of them. And now the question is, how do we add them? And we have to, and this is now a very important step, because now the plus symbol, even though we know what plus means for scalars, it is not intuitively clear what it's supposed to mean for tuples, for vectors in Rn. Of course, in 223, there was only one standard way to add two things. So I'm writing this as component-wise, and component-wise for me means that if you should write smaller. If you have, say, if a two-tuple v1 and v2, and you add this to w1 and w2, then component-wise means I just perform the operation for each component. So I have v1 plus w1, v2 plus w2. And then this is, of course, another vector. And one important requirement was the existence of a zero element or an identity for the additive operation. This was this rule right here, additive identity. So there has to be one element that if added to any other element, it doesn't change the element. And of course, for scalars, that's just the zero. But if we go to Rn, which is n tuples of real numbers, we observe that this will be actually a tuple as well, an n tuple of just these zeros. And if this is the operation here in blue to the right, then it's clear that v1 and v2 added with the 0 2 tuple is equal to v1 plus 0, v2 plus 0. Well, and then I can do component-wise. I can observe that it's just v1 and this is just v2. So in total, the vector didn't change. And so this actually does satisfy, this deserves the name of the additive identity. And it's in this case easy to check that all the axioms hold. We'll do this later. We'll have one specific example so we check the axioms. For now, I just want you to trust me that these hold, and you're welcome to go through them yourself. So if you talk about tuples, then, well, a matrix is just a tuple of tuples, so to speak. So a matrix, let me maybe go down here. So a matrix, if you have, say, a 2 cross 3 matrix, then you have A11, A12, A21, A1, no, sorry, this is A22, A13, and A23. And if you add this with B, so this is B, I'm not gonna bother writing all the indices now. Then you can also add them component-wise. So it makes sense whenever you have kind of collection of different things with components, then the best intuitive idea to add them together is just do it component-wise. So now this is the new component in the position 1, 1, and we're also going to have components A12 plus B12. And of course, this goes on. And now it's not surprising that the 0 matrix, so in 2 cross 3, the 0 matrix is the matrix of the right size with just zeros. But I mean, it doesn't make sense to add just the 0 number, but you have to have the 0 matrix to add. Otherwise, the operation that takes in 2 vectors, and in this case, these matrices are vectors in their own vector space. So be aware that this will be challenging wording. They have to be in the vector space to be added together. Oliver, you have a question?
Yeah, just a quick question. The V1 plus the W1, W2, that's an example of the additive closure belonging to the R2?
Right, yes. So in this case, you could say that this is because of axiom 1.
All right, thanks.
And so because this is true for any kind of 2-tuple, I mean, what else can it be? It's not going to be a new entry out of nowhere, because the plus is defined this way. The axiom of additive closure is satisfied. All right, let's get to the to number 4. So number 4 is polynomials of at most degree n. So anything of degree n or less is also fine. And here now it is, again, if you look at this polynomial, so this is the typical polynomial. You can kind of identify that there are, again, they're slots. So they're kind of positions, because if you specify the coefficients, the A0 to A, then you can specify fully the polynomial. And now addition and multiplication is no surprise here, done coefficient-wise. It's really just it's really just an n+1 tuple, because numbers from 0 to n are exactly n+1 numbers. And instead of writing component-wise, I just now write coefficient-wise. And the identity is as before. You just have every component to 0. But then if these are coefficients, then for a polynomial, this means that it's just this, the constant polynomial 0. This is the polynomial where every coefficient is 0. And you can verify that if you add the constant polynomial 0 to any other polynomial, then it will be the same polynomial. Lastly, I already talked about this notation yesterday. This is the set of all functions. And in this case, functions from R to R. This is not just polynomials. This can be anything. For example, I'm allowed to write that f of x equals sine x is in here. And this is far from being polynomial, because this doesn't have a top degree. This is not a finite degree. Nonetheless, it's a function. So now the question is, can someone maybe just tell me might be the operations? What can we do? Let me say that. Oliver?
Sorry, can you repeat the question?
I'm looking for the operations plus and scalar multiplication for functions between R and R. So this is a function. These are 2 functions. So this means they're just functions going from R to R. And I'm wondering how is f plus g? What does it mean just to add 2 functions? What is that?
I had my hand from before, so I'm not actually sure, but I can take a stab at it. And
yeah, that's good.
When you add 2 functions, I'm guessing you add their codomains, or to get a different codomain.
No, the codomain is unchanged, because we still want to have, I mean, this is the vector space, and we don't want to change the vector space in the addition. But it's a good guess. And in general, I encourage guessing out, because that's the only way that you actually, you try out new ideas. Mac, do you have an idea?
We could do like f plus g of x is equal to f of x plus g at x for all x and r.
Yes, exactly. So the idea here is that Wait, while do I write this now? This is absolutely correct. So I don't want to move that. So the idea is that f and g, well, what are they? It doesn't really have a meaning unless we apply it to something, unless we actually evaluate it on a number. So the really question is, I mean, not what is f plus g, but what is f plus g when we actually apply to x, where x is a real number, of course. Well, and then now everything that we have available is just f of x and g of x. So we just add them. And we call this, this is pointwise addition. And now it's not surprising that if we have alpha times f, this is supposed to be, maybe not right here, but maybe below the line. We also need to make sense of alpha times f as a function. So this is going to be a new function. But now it's not surprising that we'll also do the same trick. And we'll just say that if we have to apply this, so far just a symbol, so far nothing happened. It's just an expression. But when it comes to apply this to a number, then we say, well, now we just multiply the value. And then this, of course, is again a well-defined function. So it takes x to alpha times f of x. Any questions about this? Yes, Yuan.
The condition for multiplication is that you can multiply it by a scalar.
Yeah, that's correct.
Okay.
So this is actually very well, very good to verify. This is very good to visualize with a picture. Let me put away those things here. Maybe you just shrink them a little bit. So in this case, the analogy is very helpful because if we have a vector, then what it means to scale it is just to like tear it, to make it longer, to stretch it, or to shorten it. And I guess if you have sine of x, so if you have sine of x, and this is now considered a vector, so this is kind of weird notation, but let me just call v sine of x. I guess you have to get used to the fact that everything is a vector now. Then this should be the value 1. This pi. This is 2 pi. And then we also have, this is probably not completely correct, but this would be now 2 times sine of x. So it's just another function. And this is scaled, literally scaled. And it's also a vector because the vector space in question was functions from R to R. All right, the next step is a discussion. So I will just read the 2 questions, it's 1 and 2, and then I'll give you 3 minutes or so to think about this. Unfortunately, I haven't tried out the group discussion, the breakout groups, and last time I did this last semester, there were a lot of groups that were just quiet, so I'm a bit hesitant to do it again. But let's just try out this version where you just scribble for yourself on your own for a bit, and then we can bring it together and discuss what we're doing. So the first question is the set of 2 tuples of integers? So the difference is we don't have real numbers, but we have integers. So this would be n1 and 2, where these are both integers. Is this a real vector space? And as a hint, if you were to say yes, then you have to check all the axioms because it has to satisfy all the axioms 1 to 10. If you say no, though, it's enough to show that one single axiom doesn't hold. So be aware that that's the difference between proving something general and disproving something general. Disproving is much easier, and the best way to do it is to give a counterexample as explicit as possible. This is something I try to get into students' heads forever, and you would be surprised how hard it is to understand that disproofs are always done with counterexamples. Second part is this is not the polynomials. It's the polynomials of exactly degree n. So the difference is here in notation, this little prime symbol. So the set of polynomials of exactly degree n is the vector space. I'll give you 3 minutes now. Unless there's a question, then you may ask a question. But also, please don't spoil the answer, as I said before. There's no reason to write the answer right now. You won't get points or anything. If you want, I mean, I can copy these things. It's probably something that you want to look at right now. I don't know if you all have the slides available right now, but let me just put them here so that you can look at this, and then I'll just delete this when we start discussing it. All right. The time is getting short for this lecture, so let's continue and bring together ideas. Who has something to say about this? About, say, the first one? Gensi, is that how you pronounce it?
Yeah. So the first one, axiom 2 does not hold.
Yes, exactly. Very good. So the answer is no. And this is kind of the main question I was hesitant to put on, because it's like the only thing that's problematic here is that it's a real vector space. If it wasn't real, if we could change the scalars, then it would be vector space. But you're right. No, because
So the vector 1, 1 is in z squared, and 0.5 is a real number, and 0.5 times 1, 1 equals to 0.5, 0.5, which is not in z squared.
Yeah, absolutely correct. So this is allowed because scalars are in the real numbers. So the keyword here is real vector space. But if you multiply this with 1, 1, as you said correctly, you get component-wise multiplication. So we end up with a vector 0 0.5, 0 0.5. And this is not a two-tuple of integers because they're just in integers. So axiom 2 failed to hold. We could just make this, this would be a proof, so to speak. So this is kind of the first appearance of a proof-like structure in this course, where we have a claim, and then we just we prove the answer. And it was great that you actually gave a explicit counterexample. That's exactly what I meant with the hint. All right, now let's, can I move this again? I'm just temporarily going to move this. Can I move this down? Let me just move this up. Oh, there's still some space. Okay, what about number 2? Is this set a vector space of exactly degree n polynomials? Sidov?
Hello.
Hey.
No, I don't think so because it is not closed under addition.
Yes, exactly. Can you give me a counterexample?
Sure. So take polynomial, say x squared plus x and negative x squared. N is
yes.
2, but the resulting addition is of degree 1, which
Yes.
is a counterexample.
X squared plus x as a polynomial. Let me just call this p of x equals this, and this is in Pn r prime. Let me call the other one q of x. I'm not sure if you said exactly this, but the idea is the same.
Yeah.
So it's fine, but then if you have p, the notation, notice the notation. I'm just going to write p plus q of x, which is just done now coefficient wise, and we have the coefficient of squared 1 and the other one time minus 1. So we have x squared plus x minus x squared. These cancel, and I have x, and this is not of degree 2. This lightning is always my symbol for a problem when there's a contradiction. So this means that actually I want to say this should be a 2, not an n. Okay, so therefore this is not p plus q is not in P2 R prime. Very good. Any questions about this solution, about what we did here? If not, please lower your hand, otherwise I'm confused. Oliver, I think you just put up your hand.
Yeah, just a quick question. So for number 2, so the vector space has like why it doesn't work is because the degrees have to be the same throughout, right?
Yes, exactly.
The n, there's a fixed n, right? So
yes. So this is exactly the point. It's exactly the degree n, and I mean even another reason that this is one way to prove it. You could also say that the 0 vector, which is the degree polynomial of degree 0, is not in P2 because it doesn't have degree 2. There's many ways to prove this, but that's always the thing that goes wrong. Sam, do you have a question?
Yeah, I was just wondering. So we did this for n equals 2.
Yes.
If we were to do this for n equals 0, isn't it a vector space for n equals 0?
Yes, and do you know why?
Isn't it just identical to the real numbers?
Yes, exactly.
Okay.
Okay, so I should have said here for n greater than or equal to 0. So an observation that Sam just made is that P0 of R is equal to R. Because, I mean, degree 0 polynomials are just constants.
All right, perfect, thanks.
Okay, let me move on to the next slide. Because now I think there's 2 slides left. Let me just verify. Yes, okay, so I think we can pull this off in the last 15 minutes. So now we come to properties. This is usually the style I like to present things. We first define something, we get examples, discuss it, and then come properties. Because we need to, now that we have something new, like a vector space, we need to be able to work with it, and we need to get to know it better. And that's done by knowing its properties, its characteristics. And as I said here, just focus on this part for now. We have to be very pedantic in math because it's a very fragile discipline where we can't take anything for granted. So even though we can invert numbers, real numbers, and the real numbers are a vector space, it doesn't mean that every vector space has this property. So when we want to say that something's true for all vector spaces, we have to prove it abstractly only from the axioms, because that's the only thing we actually know for sure every vector space obeys to. So please never write 1 over v or something like this. And here are three properties that we're going to look at now to get us started of how vector spaces behave. So the first one is the cancellation property, and this seems really really almost dumb to go through, because of course we can cancel things, but this is not as given as you might think. So for vector space, that is true, but we might introduce different objects in the future, and then it will not be true. So cancellation theorem says that if you have a sum, if you have 2 vectors u and v, and if you add w to them, to both of them, then they're equal. And if that's the case, then we also know that u and v is equal. So basically it just says that we can cancel w on this equation, and we're left with an equation that is still true. Now to prove this, let's go through this for 2 minutes, and let's look at the properties that we're using here. Maybe I should, do I still have that thing? Yes, perfect. So let me just pull up this property, to the right here, maybe left, and then we can always reference what we're using. So this was a u. So now the first step we're able to do, I mean, okay, so first to tell you what the proof is supposed to be. So we assume this is true, and we want to get this equation, but we're not allowed to use anything other than what we assume, and this is that this is equal. So now to do this, the first step is we just add the 0 vector to u. And this is because of the property, which is number 5. So I'm just going to write 5 here to indicate that this is what we're using. This is extremely pedantic. You don't have to do this in future calculations, just to explain you how this works here. So if you're submitting assignments in the future, please do not be this pedantic. Okay, so now what we can do in the next step is we can replace the 0 with w minus its inverse, plus its inverse. So this is the property 6, that there's a vector for every vector that when we add them together gives us 0. So this is exactly what we're using, that there is minus w. So this is property 6. And now observe that we are now in the position we would like to actually add the u and the w first and then subtract the other w, because this is how we get the expression from above. So what we're using for this is associativity for the additive operation, and this is number 4. So it means that we can move the brackets from the right to the left. Then next step is we use the assumption. And the assumption is this on the top, where we allow to replace this with this. And in the proof, you can see that we replace this with this. And now you just do everything backwards. So we do step number, we use property 4 again, that we can move the brackets around. And then, of course, we have w minus w again. So then we use property 6 again. And lastly, we arrive at the last step where 0 plus a vector is just the vector. So this is property 5 again. And then we've shown with nothing but the axis and the assumption that u is equal to v. And this is what a proof looks like. Oliver, your hand's still up. Is that a new question or is that an old question?
No, sorry.
Okay, no problem. Any questions about this this theorem? Okay, so there are 2 more propositions on this page, but I would like to skip these for today and just ask you, this is not mandatory, but just an exercise. Just write down, so like read the proof. And write down axioms and assumptions. For each step. And when we take a break and you have questions, we can of course go over this, but for now I want to go to the next page. So this is very similar, and let's just have a brief look at what the assertion is, because that we're going to use in the future. So it says that if we have the scalar 0 and we multiply a vector with the 0 scalar, then we get the 0 vector. Again, this is very pedantic, but we have to be this pedantic. This is not something that is obvious or that is always true, because the 0 vector could be anything and multiplication could be defined as anything. So it's not really a given. Same for the last proposition. If we multiply a vector with -1, then we'll actually get the additive inverse. So notice that here in the list of axioms, we set in number 6 that the additive inverse exists, but we didn't know what it actually was. And now the proposition adds to this, so it gives us more information about this inverse, and it says that we can obtain it by multiplying it with -1. All right, last slide in the last 6 minutes. This is a discussion. So I'll give you 4 minutes to think about this on your own. The question is just really simple to state. Think about the 2 tuples again. So this looks like R2, but what we're gonna do is we're gonna redefine addition and scalar multiplication. So this is not what you've seen before on the slide. We're not gonna just do this addition component-wise, but I'm gonna say that addition is now this diamond symbol. So this is our new addition, and it works like this. So this is redefined. We're always adding this 1 here. So it's kind of, yeah, it is a new addition. Likewise, if we have a scalar alpha, and we want to multiply a 2 tuple, we don't just multiply it for each component, but what we do is we multiply the component, we add the number itself, and then subtract 1. And the question is, Is this a vector space? So that's the question in the end. And part of this question, to answer this question, will also be the previous questions. Are there inverses, for example? Are there is there a zero? I'll give you 4 minutes, and then we can discuss this. If you have questions about the question, then you're welcome to just write in the chat. Oh, there's a typo. This should be the alpha as well. All right, any ideas, any guesses or comments? Yiling?
Hi, I think there is not an additive identity, because take the original definition of the identity is that 0 vector plus a vector in the vector space equals to the vector itself.
Yes, correct.
But then using the new definition of addition, we can see that the sum is the x. Let's take v1, v2, then it will be v1 plus 1 on the first row, and then v2 plus 1 on the second row, which does not equal to the previous vector.
Yes, that is true. And you made one assumption, which is, I think you said that, let me just write down as a first guess. You tried the zero tuple, is that right?
Yeah.
Okay, so that's the That is a good guess. And as you said correctly, it will not work. But no one said that this will actually be the zero vector. So this is an assumption. This is an assumption that might be wrong. So this exercise, this is exactly the point of the exercise, is to show you that the zero vector might not be the zero tuple, so it might be different. But thank you for your participation. Jency, do you have an idea?
Yeah, so I did some calculation and found the vectors, found the thing failed axiom 7.
It failed axiom 7. 1 second. Let me just write this down. So this is not equal to v1, v2. So this can't be the zero vector. I'm just catching up, not the additive identity. Sorry, I don't know what axiom 7 is. Well, that's oh, interesting. I didn't think this would be happening, but okay, let's go through this. So let's pick maybe a different color. Axiom 7, which is that alpha times beta times v is supposed to be alpha times beta times v. So this has to be equal in order for the axiom to hold. And what we do, this right-hand side, we can just like start developing this equation from both sides. So on the right-hand side, we have a vector and then another multiplication with a scalar. And so here we have, what was it? Beta v1, beta v2 plus beta, was it minus beta? Plus. And then minus 1. And then we would do the same with alpha. And of course, then we would multiply the whole thing by alpha. So this is alpha times beta v1 plus beta minus 1. Alpha beta v2 plus beta minus 1. Oh, sorry, there's more. Then we would add alpha, and then we would subtract 1. Does everyone follow to this step? This is just the application of twice the definition of scalar multiplication. Okay, and then now we have to evaluate this. Well, this is alpha beta v1, alpha beta v2. Oh, before we continue, let's do the left-hand side first, because that's easier, and then we know we can see what's happening. I think someone's saying something in the chat. Sorry, I don't have time to read this right now because I can only focus on so many things at once. Okay, so now I'm treating alpha and beta as one number. So this is now one single entity. And that's why, sorry, this is why we now get this expression. If there's questions about this calculation right now, then just unmute yourself and ask, because then I can just comment on this. On the right-hand side, we'll just evaluate the expression that we got. There is plus alpha beta minus alpha. And then a plus alpha minus 1. And we see that indeed, beautifully, the alpha cancels. And what we're left with is alpha beta v1 plus alpha beta minus 1. And the same for the second row with v2. So indeed, axiom 7 does hold. And just as a note, V1, V2, alpha, beta, arbitrary. So if you look at the axioms, it says for all alpha and beta in R and all vectors x and v. This is equivalent to saying that we have to choose an arbitrary representation for every vector. So this could be any arbitrary vector in the vector space. Okay, let me just make one comment because, well, we're gonna take a break after this. Because actually what I wanted to say is now regarding the zero vector, the identity for addition. So let me copy this, or just cut this from here. We can put this here. And now, instead of guessing what the zero vector might be, what we can do is we can just use proposition. And I didn't give these numbers because they don't appear in the book, I think. If they do, please let me know. But I don't think it's worth giving everything a number. We just can put the fact, what the proposition says, and not its number. So it says that 0 times v is equal to the zero vector for any v in the vector space. And just be aware that this is a vector and this is a scalar. So even though they look very close, they're very similar, they're not similar at all. They just have they have similar properties in their respective vector spaces. But as we will see, the vector 0 in this case is very different. So now by definition sorry, I introduced new notation and didn't stick to it. So this is supposed to be the diamond. And here I didn't mean the I meant the star. Same here. Okay, so now if we multiply 0 star v1 v2, by definition, what we get is 0 v1 plus 0 minus 1, 0 v2 plus 0 minus 1. And when we evaluate this, this will be just minus 1 minus 1. So my suggestion, or not my suggestion, but like the proposition suggests that minus 1 is the two tuple that acts as the identity for addition here. So we could do a sanity check and just add v1, v2, diamond minus 1 minus 1. And we can continue with this after the break, but let's just take a 5-minute break and resume at 14 past with the next lecture. I'll answer questions when everyone's back so that people don't feel bad about going away. Take this time to actually walk around. I'm also going to refill my glass. Okay. Oh no, sorry. I think it's 1 more minute in the break. We just read through the chat. All right. I hope you're all back. I just finished. I just wrote down that you can finish this discussion as an exercise. Like it's not compulsory though, so it's just as a homework if you like. Andrew, you have a question?
Oh yes, sorry. Hi, Professor. Can you go back to page 9, like the polynomial of exactly
Yes.
degree n? So I was wondering if the number 0 is a element of the set P in R prime.
The well, if n is greater than 0, then no, because it does the polynomial 0 has always degree 0.
Oh, okay. So does that mean this this set also violates the axiom where of additive identity, since
Yes, correct.
set.
So actually, I can say that. So this was axiom. This is axiom 1. Fails. But also the axiom, what was it? 5. 5 also fails. Yes, correct. Oliver, you have a question?
Yeah, back to the discussion thing. So when we want to prove the additive identity, don't we start with the 0 plus the tuple equals the tuple, right?
Yes, exactly. Yes.
And but can you also do it in the other way? Can you do tuple equal to tuple plus 0? Or would that be...
Yes, that's fine, because by the commutativity relation, you're allowed to switch the order of any two vectors.
Yeah. So what would your final answer be like? Would you try to prove that the tuple equals the tuple, right?
So the tuple v1, v2, diamond -1, -1. Remember, this is equal to 0. The 0 vector, not the 0 number, is supposed to be, again, v1, v2. That's the goal. That's what you should show. And then it satisfies. So what we want to show here is that v, which is left vector, diamond, which just stands for plus in our case, -1, -1, which stands for 0 in our case, is equal to v. So this is the equation that's written in green again. the equation that's displayed here. Let me put a red box around this. So the only thing is to check what's actually the result on the right-hand side. If you have questions like these, I have more time in my office hours to go through this in detail. And we can also in my office hours go through anything that we skipped over in the lecture.
Okay, awesome.
Okay. Yeah, let me leave it at this for vector space, and I can tell you that this will be a vector space. And I guess the lesson learned here is that it can be very unintuitive that the zero vector is -1, -1, and that addition is not what we thought was the obvious addition. Right. Okay, so now it's time for the second half of the lecture. And I hope that we have time. Where did my glass? Oh, one second. I hope that we have enough time to cover all of this, but it's actually not that difficult now that we cover vector spaces, because as the first definition says right here, a subspace of a vector space. So now these are sub-objects. I don't know really how to explain this intuitively, but a subspace is a subset of a vector space, which also is a vector space in its own right. Meaning that, I mean, we've talked about subsets before. For example, we've had, what do we have? All right, yeah, I mean, example number 1 is exactly what I wanted to just say. We talked about the functions from R to R, and we also talked about polynomials. They're both vector spaces, as I explained in the previous hour. And as sets, it's pretty clear that a polynomial is just a very special function. So the polynomials, they are also functions. And so this means that Pn of R is contained in F RR as sets. Just meaning that whatever's in the left set is also in the right hand side set. The question is now, is this a vector space? And we've already seen that they're both vector spaces in their own right, which is necessary. But another important thing in the definition here is that the in the braces here, that the scalar multiplication and the addition, so the operations that the vector space have to be the same for both. So if you think of this as just this, and this is drawing. So if this is V, and this is a subspace W, then if there's a point V and say U, then it makes sense to put them together as V plus W. But then this plus operation, maybe let me just draw a plus and a multiplication sign here. They have to be the same here. So they can't be any, the red plus and minus multiplication has to be the same as the ambient space. So now what we need to check is the following. Given polynomials, P of x, Q of x, and we can just write them as, let's make life simple and just say this is A0 plus A1x, and potentially more terms, but I'm just going to pretend this is just for first order. And this is maybe B0 plus B1x. They're contained in P1R. Then addition of polynomials tells us that oh, sorry. I thought I muted everything, but apparently this time. So addition of polynomials just means that we add them coefficient-wise. So this means that P of x plus Q of x is equal to A0 plus B0. That's now the new constant, the constant term. And then we have A1 plus B1 x. But now, if you look at this, this drawing on the top, this would be functions. The blue one would be all functions. And the red one, the red subset is all the polynomials. So now, because there are as a set contained, it makes sense to think of the polynomials as functions. But now we didn't exactly define the addition and the multiplication the same way. If we're being pedantic, and I mean, this is what I urged you to do in this course. So as functions, I should write as functions and as polynomials. What we do now is we add them pointwise. So this means we write P plus Q, and then we apply, and when we apply it to a number x, we then say that this is P of x plus Q of x. Well, this is kind of unfortunate. Let me change the notation a little bit. So this is also P plus Q. And here we treat them as polynomials, and here as functions. I hope this is, it shouldn't be confusing. It's really not that hard. I think the notation is the hardest bit of this. So what we do now is we just evaluate this, and then we get A0 plus A1x and B0 plus B1x. But because we can reorder these terms, we get A0 plus B0 plus A1x plus B1x, and then we use the distributive property that we can write A0 plus B0, and we can bring together the A1 and the B1. And this is just to show you that the addition of the ambient space. So what does this mean? So the plus operation of ambient space or in this case set, as sets, it's just the ambient set, and subset agree, and that's important. But that's, I mean, technically we'd also have to do this same for the multiplication. Any questions about this? What we just so I want to make sure that this example is clear, so that you have always something in mind. So the ambient set is here. This is the ambient set, the surrounding set, the bigger set, and then there's a smaller one contained. I think superset isn't a common notation, but maybe it is. I mean, if it's clear what its meaning is supposed to be, then sure, let's use superset. There's always a bigger set and a smaller set, and we need to check that the operations which make them from sets to vector spaces agree. So there has to be they shouldn't be different. Andrew, your hand's still up. Is that a new question or is that an old question?
No, sorry, it's from before.
Okay, no problem. Okay, so basically, subspaces are nothing new. They're just vector spaces which are in a bigger vector space. That's basically all this definition really says. If you also given you a second example, this one is actually maybe easier, and I'm wondering now why I didn't start with this. So if you have a two tuple, and if you just add a 0 at the bottom, then it's a three tuple. So in this sense, two tuples are three tuples with 1 0 entry. And then again, if we have v1, v2, and 0, and we add this to w1, w2 with 0 at the bottom, then we just do this component-wise. So it doesn't matter for the operation whether we consider these to be two tuples or three tuples. If we just did this, I mean, this is now really feels very obvious, but let me just continue this. So same conclusion as above. The operations agree. What can I say here? Let me write here when subset elements are viewed as elements in the superset. The second one really is maybe even clearer. And this, I don't know, other questions? Sam?
I'm just confused how we can write that R2 is a subset of R3, because isn't R3, like the vectors in R3 a different like mathematical object compared to R2?
Well, I guess that depends on how you think of them as different. I can draw a picture if this maybe helps. Let me draw R3 and then indicate that everything that within this this plane. So this is supposed to be the XY plane. And this is really just equal to R2. So if you can view the XY plane as R2 inside R3. And this just really means that if you have a vector like this, this might be X, Y, Z, and the vector in R3. And it just means really that if you have maybe U and V, this is a vector in R2, but this is equivalent with it's the same information, the same data as having a vector U, V with 0. I should have given this a different color. Let me make this all purple. So it just means that it is confined to this plane. So this plane is a subspace of the three space. Andrew.
Okay.
So I thought in 223, right? Like when we talked about linear transformations, I thought like if we have a linear transformation from R2 to R3, it wouldn't be a 1-to-1. Like it would be a one-to-many.
That's something that's not going to be important for us for the next few weeks. So it is correct what you said, but that doesn't really matter right now. Right now, all we care about is subspaces.
Like I do remember like the instructor for 223 saying that R2 is not a subspace of R3.
Well, it certainly is. I hope that instructor, or maybe that was something misunderstood, but it is certainly subspace of R3.
Okay, thank you.
And really, it maybe intuitively it was the different context, but in this definition, it really is clear that it's a subspace because we can embed. We have a way of thinking about the two tuples as three tuples when we add the 0, and the operations of the bigger subspace, the R3, which is subspace as we saw in the previous lecture, really do make sense also for the two tuples.
Oh, okay. Okay, thank you.
All right, so let me give you this discussion, and I see there's the one hand up, but maybe I can reply to this in text while everyone else thinks about this discussion, because we only have 25 minutes left. So if we suppose that V is a real vector space, then the question now is, first of all, can U be empty? Is the empty set allowed to be subspace? Second of all, if we want to show that U is a subspace, what kind of axioms from the 10? So this refers to the 10 from 1 to 10. Which of these are already satisfied by U just by having the same operation? And then as a follow-up question, which kind of axioms do we still need to check? I'll give you 3 minutes for this. All right, let's discuss number 1 first. Yiling, you have your hand up.
Yeah, so I think by definition, a vector space must contain at least an additive identity.
Yes, correct.
So the you cannot be empty in this case.
Yeah, exactly. But actually, just as an added information, the set just containing 0 is a subspace. A subspace of every vector space. Okay, very good. So let's come now to the second and third part, and I think we can just do them all in one go. They're the 2 last questions. Maybe one thing that wasn't obvious from what I had said so far about subspaces, the usual way, the usual approach is that that U and V, so if V is a vector space, declared as a subset with condition. And we've talked about this yesterday, so that, for example, I can realize that this notation might be a little bit stupid to use, but that, so the even integers are just defined, or just like explained to be all integers with the condition that n is even. So usually you have a subset without an operation. That's why these 2 examples are kind of not the standard norm, because these subsets already had an operation. So now, just as a warning, usually we have a subset and then the operation is obviously the same. So now if we assume that use a subset and we want to have the same operation as in V, then the question is which of these axioms automatically hold and which are not automatic. Mac, your hand is up.
Well, I was gonna try to answer the other questions.
Which other
for, like,
questions?
2 and 3. Which axioms?
Yeah, that is 2 and 3.
Well, I was gonna say that you don't have to you don't have to check axiom 3 to 10.
You don't have to check axiom 3 to 10. Okay, that's already a lot. Let me go through them one by one. So 3 is correct. I agree, because the reason, let me just comment on this a bit, briefly. The reason is if you have 2 elements, so if x, y are in U, then also just because U is contained in V, they are in V, and then for V we do know that 1 to 10 is correct. So then this is equal, this commutes as an operation in V. So whenever this is the kind of trick to all to these axioms and the discussion right now, if you can embed them in the larger vector space and then the axioms hold, well, then the axiom is still satisfied in the subset. Same arguments. So this is specifically for 3, but you said 3 to 10. 4, yes, I agree. 5, I don't agree with. Multiplicative associativity, yes, I agree. I agree. I agree. I agree. So basically, I agree to everything except for 2. Oliver, you have your hand up too.
I just have a quick question on 2 parts, but for the first one, since it's a real vector subspace, it has to, real vector space, the 0 vector must be in it, right? Therefore, number 1, it doesn't have a correct conclusion because you has to have a 0 vector, in it, so that's why it can't be empty, right?
Yes, correct.
Okay. And for this one, since we don't know if it's a polynomial or tuple, we don't know that if it already has operations. Like in the other one, you were saying that since it already had operations of additive closure and multiplicative closure, it could the subspace agrees with the operations, but this time it doesn't because we don't know.
Well, my comment was the following. We're going to impose the same operations, but we want to see if it's still a vector space. The other examples on the previous page were the opposite. They were a vector space for sure, but maybe not the operations agreed. Now the operations are opposed, so like we pressure these operations, give you the same operations. Is it a vector space? So there's no question what the operation is. And maybe so suppose you had the integers and then you opposed only to take the even numbers. Then the operation, if it was defined for all integers, it would also make sense to only apply to the even numbers. So the operation is clear. It's going to be the same as in the superset. The only question is, does it satisfy all axioms? And is there someone else who has an idea? Mac, do you want to continue?
Oh, no, sorry, I just forgot to lower it.
Okay, so let me then just give away the answer that this is not clear. This is not clear. And same for the identity and the inverse. These are not automatic. And the reason is, well, does it make sense to skip the next page for now? Right, so let's only look at number 2. In fact, let me crop this. Let me copy this and just put it down here. And just give it a quick example. So example of a subset. U in a vector space that is not a subspace, because I guess you haven't seen non-examples so far. So I want to show you to demonstrate that it actually can go wrong. So we've talked about matrices before, and this is a vector space. Oh, sorry, it's not relevant for this course. This is now V, and this here we're just going to call U. It is a subset. It selects certain matrices as I described. There's a condition, and that's pruning out certain matrices that are not invertible. So now the question is this a subspace? And so first of all, U has has or let's say for A and B in U, invertible matrices, A plus B still makes sense. There's no question that addition of matrices works no matter what. The thing though is that 1, 1 is, so now in this case, I'm going to specify 2 by 2 matrices from this point on, just because the notation is easier. This is in V, sorry, U, because it is invertible. So is -1, -1. Same reason. But if you add these two, you're leaving the subset that we just specified, because this is the 0 matrix, and this is not in U, because not invertible. So the story here is that we are able to define in a vector space. Let me just write v dot sp for vector space. We're able to define a subset, and we can look at elements A and B in here. And the operation does still make sense, because if we forgot about the subset, we would just see one giant vector space with 2 elements, and then the operation is just no problem. But then it's possible that if A and B are here, that A plus B is here. There's no guarantee for a subset that it's going to stay in the subset. There's just no reason for it to do that. Okay, does that make sense? So this is this means that axiom 1 is not automatic. While we edit, let me also say that axiom 2, no, sorry, which one was it? 5? 5, right. Number 5 isn't automatic either. Simply because if you have U to be all the vectors in V such that there's some condition, maybe the 0 vector, so the 0 that exists in V, because we know that V is a subspace, might not satisfy the condition. I mean, it just really depends on the condition. In this case, it doesn't, because the 0 matrix is not invertible. Okay, Oliver, you have a question.
Yeah, so what I can concur from this is that all the automatic ones always satisfy the condition, but the non-automatic ones are restricted to some conditions that, and if they're not, they may not actually satisfy the condition.
Yes, exactly. So basically, the opposite of this exercise discussion is some of them we don't need to check for subspaces, because from the definition, we just say it has to be subspace in their own right. That means technically go through axioms 1 to 10. This discussion, though, tells us that, wait a second, if you do 1, 2, 5, and 6, that's actually enough. The other ones are automatic. Okay, so we have now 6 minutes left, and I'm debating how to what to do in the last 6 minutes. There are a bunch of examples, but the problem is that we need this theorem before we actually do the examples. So even though I kind of want to give you more examples and more intuition about this, it is kind of necessary right now that we do this first. The other order just doesn't make sense. But then you can look at this at, on your own, and this is actually, these are the two last slides. So we can start next lecture next week, and then we can also talk about this in my office hours with exactly these examples, and then you will have a much more intuition about subspaces. Okay, but now first of all, this theorem, and this theorem kind of uses what we just observed, and it even makes it even better. So it's boiling down these four conditions that are still open for subsets to be subspaces to even less conditions, only two conditions. So this is a very powerful tool, and this is why I want to discuss it right now. It says that if we have a vector space, as always, we call it V, and a subset U, then there's actually just two things we need to check to make sure that all the 10 axioms of a vector space are satisfied for U. So this is a subspace if and only if, first of all, it's not empty, and second of all, any two vectors, U and V, and a scalar alpha, combined to alpha U plus V is in U still. That's enough to guarantee that this is actually a vector, yes, a subspace. Okay, and the proof is actually not too hard. It is abstract, but let's just go through this. So we need to wait a second. We need to show that the let me call this in quotation marks open. With this I mean not automatically satisfied axioms. I believe it was number 1, 2, 5, and 6 follow. Let me just double check. Yes, indeed. Okay, so the first one is, and we can use these as given. So the first step is to assume that there's some vector because it's not empty. Okay, very good. Now the second thing we want to show is that that U actually contains the 0 element. So 1 second. Right. So because we know that for any vector space, V is a vector space, we know that -1 times V is equal to minus V. And by assumption, we'll choose alpha to be -1. And in this equation here, I'm now using this equation. And then we can write, switching colors. then by assumption, -1 times v plus v is in u. That's exactly the form that is in this equation here. So I'm just choosing specific and specific terms for these. So alpha is -1 and both vectors are the same. But what is this? So this expression is minus v plus v equals 0. So we have shown axiom, which one is this? I think this is 5. Yes. Next, we need to show that the inverses are in there. But this is also simple. Now that we have the 0, we can choose one of the vectors in this expression to be 0. So we use the same expression again with alpha in this case again -1, v and 0. And then we add that alpha, just write this, getting hectic towards the end. I'll be done in 3 minutes. I know that I'm over time, but I'm going to just finish this and then we'll end the lecture. So we know that the expression -1 times v plus 0 is in u, but this is just minus v plus 0, which is minus v. So I don't know if this is clear to everyone, but I'm reusing this green expression that is that I highlighted in the assumptions because this is of and this is also of the form. I'm just rotating the elements I put in here, so the vectors differ, and from that I'm able to draw different conclusions. And step by step, I'm getting more and more out of this. So first I did axiom 5. Now I did axiom 6. So because this v was arbitrary, this means now minus v is in u for all v in u. So this means this axiom 6 is verified. Well, and now we're almost done. The only last thing is to check that axiom 1. So we just let alpha to be 1. Then uv, just any elements. And then the green expression, which we recycle now a third time, is u plus v. The 1 disappears because this is property 10 that multiplying with the number 1 always gives 1 is in u. So this axiom 1 is checked. And then lastly, we just one last time we'll write alpha in R, and this will be axiom 2. Any alpha in R, we're going to take u in u and v to be 0, and then we write again this this equation, either this term, and what we get is that alpha u is in u. So axiom 2 is checked. And then from the previous discussion, we know that all other axioms are already satisfied. We conclude that U is a subspace. Okay, sorry for going over time. I'm done with this proof now. I'm happy to stick around for a few minutes if there are questions. If you need to go right now, the next slide will be examples. So unfortunately, we didn't get to that. But if you want, you can look over this yourself, or we'll just start. I mean, we anyways can start next week with this. And I hope this will give you some intuition of how this works. But I really wanted to get this theorem through first, because now we're able to much quicker decide if something is a subspace or not. Yes, thank you for your attention. If you need to go, then this is the end. But there's a question by Daniel. Please go ahead.
Yes, I had a question about the structuring of the proof. And I forget which page it was on. Let me just find the page real quick. So,
there were only 2 proofs in the lecture, I think.
there was one, I believe, about about vector spaces. I think it was proving one of the axioms. Or yes, it was on page 10. The proof on page 10, the theorem of cancellation.
Yes.
I was just a bit curious about the structuring of that proof, because could we start the proof off from the assumption? Because we're assuming that vector u plus vector w is equivalent to vector v plus vector w, right? Could we start our proof off that assumption and then kind of go like, I want to say backwards, but go in reverse? So we do assumption and then go from the axiom 4, then 6, then 5, or do we have to go from the very top like you did, where we start with axiom 5 and then go all the way down?
I see. So you would want to start with this equation on the top.
Yeah.
And then you would want to subtract, I guess, w from both sides.
Right. Is that like a proper proof structure? Because that's kind of like how I interpreted proofs to be like in my other classes. But if this class is different, like form, that's
no. Like math is always the same. There's no different proof techniques.
Okay.
I think the reason why this is a standard way to writing this down is because it's a very neat way to write it. Observe that here we just start with the left hand side. We do some axioms and stuff, and then we end up with the right hand side. So this is a very nice way to, if you were to put this into a black box, not everything, but just this. If this was a black box, you would have exactly u equals v in just one continuous sequence of equalities.
Right.
Whereas if you start with u plus w equals v plus w, you'd have to somehow write, well, I'm subtracting w on both sides. You have to say, well, the inverse exists, and then you would have to say, well, actually, we can just let me just write what I'm saying. So what would you do is you would write this equation, and then you would say there exists minus w. So we add this to this previous equation. So you would write this. But because we're being pedantic, we have to put the parentheses around the previous term because you're subtracting it from both.
Right.
And then you would technically do the same hocus pocus. So you would also do number 6, which allows you to move the parentheses on the other side.
And then we get cancellation.
Then we use number 5, where we have u plus 0 equals v plus 0, and then we would do.
Would there be an
no?
X
Sorry,
or would it just be u equals v here?
Sorry, I think this is the right numbering.
Okay. Yeah.
But then we would get u equals to v. So yeah, this is also true and definitely valid as a proof.
And just one more
Um,
thing about this format, if you don't mind.
Yeah.
Do I have to write there exists a negative vector w? Because wouldn't minus vector w just be a scalar multiple of the vector w by -1? Would I have to write there exists minus w, or is that a
Yes, you do have to write
Okay.
this.
Right.
I mean, if it's a vector space, this is one of the axioms that there exists an inverse.
Okay.
If it's just a subset of a vector space, then you would not have this. So you have to really emphasize that you're using this axiom.
Okay.
Not for like the rest of the course. It's just for this first 1 or 2 weeks that we want to really make sure that we, I don't know, that we emphasize what is given and what is not given.
Yeah. Okay. Thank you very much.
Sure.
Have a great day.
Welcome. Any other questions? I'm going to write here that this is an alternative. Yuan, you have your hand up.
For the question where it says, is the set of polynomials of exactly degree n? It was probably at the top.
Oh, right. That was a vector space question, I think. Yeah, here.
It fails axiom 1, so it's not closed under addition because we gave an example where like the solution was like 0. And
the solution was x. So we have two polynomials. We
yeah,
have
so,
x squared plus x and minus x squared, and the sum of them is x.
so if R1 is a subspace of R2, then wouldn't x also be part of R2 if it's part of R1?
Well, R2 doesn't appear here. This is polynomials of degree 2 with real coefficients.
Oh yeah. Okay, never mind.
Okay, sure. Any other questions? Okay, then I'll end the lecture here and I'll upload this to YouTube again and add the notes. See you next week.